heavy bomber squadron takes off on a long-distance operation against the enemy. Flying with great speed at high altitudes, they avoid detection, drop their loads, and are off for home before enemy fighters and pursuit planes can possibly climb 25, 30,000 feet or even higher. In these cold substratosphere regions of the sky, where the air is so thin, it affects engines as well as men, the fastest enemy planes are no match for our B-17 or our B-24s, which return safely to their bases.
Air supremacy is a vital factor, perhaps the deciding factor in this war. The achievement of air supremacy involves speed, personnel, firepower, and maneuverability. But one of the most important factors is the ability to achieve maximum altitude without the loss of power. The Civil War maxim of getting that fastest with the mostest men can be revised in the terms of military aviation to getting up higher with the mostest fighting power.
This master of the skies, the dynamic turbo-supercharger, is the reason for our air superiority at high altitudes. For the year 1941, the Collier Trophy, one of the highest honors in aeronautics, was awarded jointly to Dr. Sanford A. and the Army Air Forces for 25 years of collaboration in perfecting the turbo-supercharger, which is playing a leading role in sweeping our enemies to defeat. The turbo-supercharger makes possible high-altitude flying with full engine power. An airplane engine derives its power from explosions of a mixture of air and gasoline. At altitudes above sea level, the air gets thinner and thinner. Therefore, these explosions get weaker and weaker. At 20,000 feet, an unsupercharged airplane engine gives but one-half its normal power. At 35,000 feet, only a quarter of its power. The turbo-supercharger counteracts this loss of power by compressing and cramming air into the engine, thereby maintaining proper manifold pressure to give full power at high altitude. It performs the same service for engines that oxygen equipment performs for pilots, kidding the engine into thinking it is always working at sea level. Without a turbo-supercharger, the engine gasps for breath. During World War I, the first model turbo-supercharger was tested under great difficulty. On a truck at the summit of Pike's Peak, 14,100 feet above sea level. The Liberty engine developed 400 horsepower at sea level, but moving up to 14,000 feet, it dropped to 265 horsepower. Then the turbo-supercharger not only boosted it up to 400 horsepower, but to 410, or 10 more than normal at sea level. The turbo-supercharger has demonstrated its worth in actual combat all over the globe. Our great bombers, the Boeing B-17 Flying Fortress and consolidated B-24 Liberator, together with the Lockheed P-38 Interceptor, the P-43 Lancer, and the deadly Republic P-47 Thunderbolt, are all turbo-supercharger equipped, which enables them to fly and fight effectively at great heights above the earth. Our turbo-supercharged interceptors and pursuits can get on top and stay on top of anything the enemy has to offer. These tactical advantages are the key to air supremacy and ultimate victory. Turbo-superchargers permit our bomber pilots to avoid bad weather, even storms, by climbing over them, making it possible to fly at altitudes and speeds which result in maximum engine efficiency. Obviously, we have a decided edge when we can bomb the enemy with a minimum of danger to our planes and personnel. Flying turbo-supercharged planes, our boys have bombed enemy objectives with amazing accuracy from heights where they were invisible and unheard from the ground. There had been no warning sirens, no opportunity to take shelter, only the sudden scream and paralyzing crash of falling out of a clear sky. Almost without exception, these planes have returned safely from their mission. Time after time, you have read of our big bombers returning unscratched from perilous raids in all theaters of the war. It is true that our heavy bombers have been in dogfights, have suffered casualties in men and planes, but in practically every instance, this has happened when planes were operating at levels below 25,000 feet. Another reason we have to get up higher and higher is to get above the effective range of anti-aircraft fire, which has been reported even above 30,000 feet. All combat planes are equipped with gear-driven superchargers, which are built into the engines and driven from the engine crankshaft. These geared superchargers are effective up to medium altitude. At high altitude, the turbo supercharger is needed to provide additional pressure to maintain full engine power. With proper care in installation, maintenance, and operation, the turbo supercharger is extremely effective, reaching its full power and efficiency at 25,000 feet or higher. This is the turbo supercharger installation in the B-17. Installations vary according to the different types of ships, such as the B-24, the P-38, the P-43, and the P-47, where it is submerged in the fuselage. A turbo supercharger is driven by the terrific impulse of hot exhaust gases from the engine. It largely uses waste power. Waste exhaust gases pour into the nozzle box, where they are directed onto a metal windmill or turbine wheel at 1,500 degrees Fahrenheit, with all the red-hot energy that implies. This blazing force spins the turbine wheel at terrific speeds, up to about 20,000 revolutions per minute. The turbo supercharger stands the gaff of almost impossible high-speed strains and stresses, and still performs its tasks at temperatures ranging from 1,500 degrees above to about 67 degrees below zero Fahrenheit. The basic principle of all turbo supercharger installations is outlined in this diagrammatic drawing. Flexible joints are installed between the component parts to absorb vibration. For purposes of clarity, we will divide the system into 5 parts. 1, the induction system. 2, the exhaust system. 3, the ventilating or cooling system. 4, the control system. And 5, the lubrication system. Individual installations vary according to the different design of ships, but their functions remain the same. The induction system comprises rammed air intake in the engine nacelle or in the leading edge of the wing. The speed of the plane rams air into these intakes and assists in keeping up pressure. Ducts carry this air to the compressor, where it is compressed and forced through the intercooler, and the carburetor to the inlet of the geared supercharger. The geared supercharger is used to do part of the required supercharging and to improve the distribution of the fuel charge to the cylinders. The exhaust system takes the high-temperature exhaust gases from the engine to turbine wheels or out through the wastegate to the atmosphere. The cooling or ventilating system cools the supercharger parts, thus preventing damage due to the high-temperature exhaust gas. Rammed air is carried through ducts to the turbo, where the stream is split by the baffle plates and cool air forced against the bearing housing, compressor casing, the back of the turbine nozzle box, and the back of the turbine wheel. Other ducts perform the same functions in relation to the exhaust stack shroud, which insulates the exhaust stack, and the air intercooler, which for proper combustion reduces the temperature of the air fed from the compressor to the engine. The intercooler cools air in the same way the radiator on your car cools water. The cooling cap supplies air to the rim of the turbine wheel to lower temperature of the wheel disc. The turbo supercharger is controlled by a hydraulic regulator, which operates the wastegate in response to pressure changes in the exhaust stack. The wastegate control is adjusted by a boost lever in the cockpit. The wastegate controls speed of the supercharger by bypassing the gases around the wheel. With the wastegate open, the turbine will idle. Closing it by degrees enables the turbo supercharger to operate at required speed. Lubrication is accomplished by a gear-driven pump. One element of the pump takes oil from the tank and supplies it under pressure to the moving parts. The second, or scavenging element, returns the oil to the tank. When a ship comes in from a long, grueling flight, or even a routine operation, the pilot knows that the ground crew will assure the success of his next mission by a thorough inspection. The inspection of the turbo supercharger installation is performed in accordance with Army Air Force's technical orders. Air ducts running from the cells or from leading edge of wing must be kept clear at all times. A piece of newspaper in a ram air duct will choke off cooling air, which is absolutely necessary for proper performance. Men are sometimes careless and step on louvers, blocking the flow of ventilating air. Ducting must be examined for broken connections, cracking, and chafing. The exhaust system is equally as important as the air feed. All joints in exhaust system must be inspected for gas leakage, with special attention to flexible joints. Look for signs of overheating and leaks around exhaust piping. One small leak might rob the engine of that vital extra few miles an hour which marks the difference between victory and disaster. Leakage can be detected when the engine is started. In the lubricating system, check oil level in the tank. Keep all foreign matter out of oil. Note and record excessive oil consumption. Keep oil tank vents clear. Report signs of oil foaming or mist. Inspect all pipelines and connections, including turbo supercharger regulator, for oil leakage and security. When inspecting the control system, check free movement of regulator in relation to open and closed positions of wastegate. Check free movement of boost control in cockpit. Be sure turbo regulator locking device operates correctly. The pressure regulating pipe should be disconnected at both exhaust manifold and regulator. Blow air through and record any water condensation, carbon, or other foreign matter. Water will freeze and foreign matter clog the pipe. Test pipe to make sure there is no leakage. See that regulating pipe orifice in exhaust manifold is free from carbon or corrosion. Inspect turbo supercharger to see that it is firmly in place. Inspect nozzle box for deformation or cracking. Turn turbine wheel by hand, feeling for any obstructions or tight spots. Listen closely for strange noises or rubbing, which might be caused by foreign matter on back of wheel. Examine wheel for signs of overheating. Inspect buckets for alignment and deformation. The cooling cap is always taken off and is replaced by a cover cap to protect the turbine wheel. The turbo supercharger is carefully lowered from the plane and starts its journey to the overhaul depot. At the depot, the supercharger is placed wheel down on a special stand for disassembly. After proper clearances are taken, the rear compressor casing and gasket are removed, revealing the impeller and diffuser. The impeller is on the same shaft as the turbine wheel and discharges air through the diffuser to the compressor casing, which collects the compressed air and feeds it to the engine. After removing the impeller, the front compressor casing and diffuser are taken off as a unit. Note that we are working from rear to front, as the turbine wheel side is always called the front, regardless of position. This disassembly appears very simple. Actually, it is a long and careful process, which we will demonstrate by the more detailed removal of the rear bearing and its housing. Safety wires are cut and the 3 retaining screws taken out. The rear bearing clamp washer is lifted off, and the same 3 retaining screws inserted in the threaded jacking holes in the flange of the rear bearing housing. Each of the 3 screws is turned a little at a time, one after another, thus evenly jacking out the rear bearing and housing. The rear bearing is a ball bearing. Next, the bearing and pump casing is removed. The oil pump is operated by this drive sleeve, which is locked onto the shaft with the Woodruff key. Then the front bearing, which is a roller bearing, is removed. The baffle plate is a radiation shield and also divides and directs ram cooling air against the bearing and pump casing, front compressor casing, the back of the turbine nozzle box, and the back of the turbine wheel. A series of blades in the nozzle box directs the high-temperature exhaust gases onto the buckets of the turbine wheel. These buckets are separate blades driven into slots in the wheel. During disassembly, 5 clearances are taken. 1, annulus. 2, blade side of impeller to rear compressor casing. 3, plane side of impeller to front compressor casing. 4, pump backlash. 5, between turbine wheel and nozzle box. Here are all the parts of a turbosupercharger. The disassembly you have just seen in a minute or 2 actually takes a skilled mechanic several hours. After disassembly, careful inspection is made of all parts to determine those which are to be repaired or replaced. One of the most precise repair processes is proper balancing of the rotor unit. This balancing is necessitated by even minute differences in the parts as placed on rotor assembly. The rotor unit is placed on the balancing stand where it is dynamically balanced. Running at speeds in excess of 20,000 RPM and in any position which the plane flies calls for more delicate balancing than a fine watch. A daub of clay is placed on the wheel, then shifted to find the point at which vibration becomes negligible. Then, from the diametrically opposite side of the wheel, enough metal is removed to offset the weight of the clay. The same balancing procedure is used on the impeller end of the rotor unit. And enough metal is removed to balance the impeller. After balancing of rotor and assembly of supercharger, it is ready to be returned to the flying field. Like every other part of a modern military airplane, the turbosupercharger must be understood by pilots who should remember important instructions regarding control. Before starting the engines, be sure that the turbosupercharger is in the off position. No provision is normally made to supply engine air except through the turbo, its ducting, and intercoolers. Therefore, considerable resistance will be imposed on airflow to the engine when the turbo regulator is in the off position. In order to obtain sufficient manifold pressure for takeoff power, it is necessary on some airplanes to use a small amount of turbo boost. Close the wastegate a little. Tactical requirements may dictate using military rated power for a period not exceeding 5 minutes. Climbs are usually made with about normal rated power. Small adjustment of the turbo control may be necessary during climb to keep manifold pressure at the desired level. For low altitude, low power cruising, when the geared supercharger is enough to provide proper manifold pressure, reduce engine throttle to maintain the desired manifold pressure. At high altitudes of more than 20,000 feet, it is not practicable to operate at very low engine speeds and powers. Turbosuperchargers should be kept engaged at all times when induction system icing may be encountered. Above approximately 25,000 feet, manifold pressure should be reduced in accordance with the instructions given for each type of plane to avoid overspeeding the turbosupercharger. For gliding and approach for landing, the turbo regulator is set approximately at maximum cruise position to ensure power to go around the field again if necessary. The performance of ships equipped with turbosuperchargers is a matter of teamwork between ground crews and pilots. It is not necessary for a pilot to learn all the mechanical details of construction, but it is for him to know what he can expect from a turbosupercharger when he needs its assistance to win the fight, save the lives of his crew and himself. The men who fly these powerful planes are going to depend upon their turbosuperchargers in emergencies which will test all their skill, strength, and courage. Operation and control are largely automatic, but there are certain times when the pilot needs power and needs it instantly. These times occur under stress of actual combat conditions, and his reaction should be instinctive. The pilot will depend upon this master of the skies to give him the edge of speed and maneuverability, which means the difference between defeat and victory in the substratosphere regions of the sky. It is with enormous pride in American scientific invention and mechanical ability. Look at our interceptors and pursuits, which can get on top of anything that flies. It is with a feeling of grim satisfaction that we know our bombers are able to shoot down or escape from anything the enemy can put in the air. This edge is held only as long as the turbosuperchargers on each and every one of these planes is kept at the peak of performance. They must answer every demand that the pilot makes. It's up to the ground crews to keep them flying, and flying higher and higher. Ride the master of the skies to victory.